It's time for another math easy solution, and today we're going to go over further into the vectors and geometry of space video series, and this time look at the dot product, which is a very useful concept in physics and mathematics in general. Anyways, let's continue further. So as always, if you don't have time to watch this whole video, you can play this video at a faster speed. Top secret life hack: your brain gets used to faster speed. There's a link to a tutorial I did on that. And you can also download and read the notes, or read the notes on the Hive blockchain. All the links will be in the description below. You can also watch a video in parts, and all the timestamps of all parts are going to be in the description. Anyways, let's jump right ahead. So calculus book reference. Note that I mainly follow along the following calculus book. This is the Calculus Early Transcendental, 7th edition by James Stewart. And note in the earlier videos, I used the 6th edition, just in case you're following along either of the books. Alright, and now let's take a look at the sections in Calculus book chapter. So I made a list of the sections in this particular chapter with links to the Hive post, and has links to all the videos, all the video platforms that it has, such as YouTube, 3Speak, and Odyssey, and so on. So with links to the Hive post of the videos I've already finished. So vectors and the geometry of space chapter in my calculus book. The first video I did on 3D coordinate systems, then on vectors, and then I also did a video, very interesting one, on complex numbers as rotation matrices. So I highly recommend diving into that one. And then now the one we're doing right now is the dot product, and that's the current video. And then later we'll go over these ones here as I go through. So let's jump right in. So topics to cover. So note that the timestamps will be included in the video description for each topic listed below. So the first part, we're going to go over the dot product. Then definition 1, it's on the dot product. Example 1. Then go over properties of the dot product. Then I'll put proof of property 1, proof of property 2, proof of property 3, proof of property 4, and proof of property 5, etc. And again, I'm listing all this because I'll put this in the description with links or with the timestamps to every single section here. Then go over definition 2, dot product, example 2, corollary or a corollary, and then example 3, example 4, and then direction angles and direction cosines. And look at example 5, and then projections, and then look at vector and scalar projections, and then summary of projections, and then example 6. Then look at the next section, or the last section, vectors in physics, and go over 2 examples, example 7 and example 8. Alright, so now let's finally jump right in and look at the dot product. So far we've added 2 vectors and multiplied a vector by a scalar, and that's in the earlier videos on the on vectors and so on. We just added vectors and we multiplied vectors by a scalar. But then the question arises, is it possible to multiply 2 vectors so that their product is a useful quantity? And one such product is the dot product, whose definition follows. And another is the cross product, which is discussed in the next section. Or actually, this is from my calculus book, so in a later video. Alright, so now let's continue further and look at now definition 1. So we'll define dot product, and we'll show how it is we could utilize it to be basically a useful concept, a useful quantity. So if the vector A, and remember we bold them if it's a vector, has components A1, so you write these triangle brackets for indicating it's a vector. So A1, A2, A3, and this B vector has components B1, B2, B3. Then the dot product of A and B vectors is the number A dot B, so you have this dot there, given by, and we'll write this over here. So this is A dot B, and remember the notation. You could also write a vector with an arrow on top, and I'll write it with arrows on top when I'm writing with my pen, just because it's hard to write with the bold setup here, because they all look the same. This one here, so that's bold. It's easy to bold when you type, and not so easy when you're when you're writing. So this is the definition. This one is we're going to have the components multiply the A1 by B1, then A2 by B2, then A3 by B3, and then add all of them up, and we're going to get this. So we're going to get A1, B1. This is the definition, and then we're going to show that this is an actual useful quantity, and this is going to be A3, B3. So notice what we have. We have two vectors multiplying or dot product together. So the dot product of two vectors is just a summation of these three multiplications. In other words, this is just a real number or a scalar. All right, so thus, to find the dot product of A and B, we multiply the corresponding components, as we did over here, and then we add them all together. And again, as stated earlier, the result is not a vector. It is a real number that is a scalar. For this reason, the dot product is sometimes called the scalar product or inner product. And although definition 1 here, so that's definition 1, is for three-dimensional vectors, the dot product of two-dimensional vectors is defined in a similar fashion. So if you have two-dimensional vectors, so A1, here's the components of them, just call this A1, and then this is A2, dot product of the second vector B1, B2, so this is a two-dimensional one. This just becomes, well, A1, B1 plus A2, B2. So just the components and so on. You can do this for any number of dimensions, I believe. All right, so now let's take a look at an example. So this is example 1, and this just has three different dot products for us to exercise. So we have this this vector, this two-dimensional vector 2, 4, dot product 3 times, and then 3, and then -1. And the other one is these ones over here. And yeah, let's just go over each one. Let's go over the first one here, which is 2, 4. All right, so let's look at the solution. Let's go over it. So 2, 4, and then dot product 3, -1, these two vectors. So this equals to, well, 2 times 3 plus, and then the next one's going to be 4 times -1. And this equals 2, well, it's just me 6, and then 6 minus 4, this equals to 2. All right, now the next one here, let's write that down. That is going to be -7, -1, 7, 4, dot product with the three, these are three-dimensional vectors, 6, 2, -1, 2, like that. All right, and then this is going to equal 2. Yeah, it's going to equal 2. Well, now we have a three-dimensional dot product, so we multiply this -1 times 6. So it's going to be -1. I'll put this in bracket. -1 times 6 plus 7 times 2, 7, 2, and then 4, and then -1/2. It's going to be times 2, and then plus 4, -1/2. Let's add all these together. So this equals 2. Let's put it here, actually. Make it in line. Equals to -6 plus 14. Then this cancels, well, 2. Or yeah, that's going to be 2. This cancels. This can be, well, yeah, 4 divided by 2 is 2, and then -1. So -2. Like that. So that's going to be -8. Or you could just look at this together. What are these together? -6 plus 14, or 14 minus 6 is 8. 8 minus 2 is equal to 6. Like that. All right, that's pretty epic. So now let's take a look at the next one. This one is using this the standard basis vector form. And remember, recall from earlier video. Yeah, from the earlier video, these ones, each one of these is, for example, this one here is just 1, 0, 0. Vector. This the J1 is 0. Then you put a 1 in, like that, and similar for this one is be the K. This would be 0, etc. So it's each components of those, so, etc. What this essentially means is this is the same as writing 1, 2, -3 in this components, but you're writing it as standard basis vector setup. And notice the bracket change because we're writing it in these vectors. Setup. So what this equals to, well, let's just write this down. So we have the vector there, the I vector plus 2 times J vector minus 3K vector. This times by 2J minus K vector. This equals 2. So now this is the interesting part here, because this one skipped the I one, and that's because it's assumed that the I is there's 0 times by I. So in other words, when we do the dot product of these two, this I, this is going to be 1 times by, well, there's the 0 is gone there, so we'll have a 1 times by 0, and the next one's going to be plus 2 times by 2. There's the J's match up. 2 times 2. And the next one here, negative 3 times by, yeah, this one is just a negative 1 there. So we have a negative 1 like that. So this equals 2. Well, this is going to be 0 plus the next one's going to be 4. 2 times 2 is 4. Then the next one's going to be 2 negatives becomes positive plus 3. So in other words, this equals to 7. So there's the dot products for all 3 of these. So all these vector multiplication or dot products, and then we get scalar numbers, just real numbers. All right, so now let's continue further, and now basically look at some properties of the dot product. So the dot product obeys many of the laws that hold for ordinary products of real numbers. These are stated in the following theorem. So properties of the dot product. So if the vectors A, B, and C are vectors in V3, or it's just a set of all three-dimensional vectors, and C is a scalar, then you'll have these 5 properties, and these properties are listed as, well, property 1, A dot A equals to the length A squared. So the vector A, the distance or the length of it squared is equal to just when you have a dot of itself, so A dot A. And now this property 2 has A dot B equals to B dot A, so you can reverse the directions. You could switch up which one starts first. And then property 3 is A dot, and then B plus C is equal to A dot B, so you can multiply this inside, plus A dot C. And then property 4 is, this property 3 is just like a real number. You could just, real products. You could just multiply this out and spread it out, and so on. So property 4, scalar times A, and then the dot product with B is equal to, and you can just factor out the C, equals to C times it by A dot B, which equals to, you could also put the C inside here. So you could have A dot C times B. And property 5 is if you have this 0 vector dot B, this just equals to 0, a real number. So it's a scalar number. Very interesting. And now these properties are easily proved using definition 1, and they are proved below. Alright, so now let's take a look at proof of property 1. That's A dot A equals to the length A squared. So let's take a look at that. So you have A dot A, and we'll do this in 3 dimensions. This equals to, well, this is the same thing as writing A1, so it's 3 components, A2, A3 dot, and then it's going to be itself, so A1, A2, A3. So we just apply the definition of a dot product. This just equals to, well, A times A1 times A1, that's just going to be A squared. Then the next one's A2, it's just going to be A squared plus A3 squared. And this just equals to, well, this is the length formula. This is just the components of a vector squared. In other words, that's just going to be our A vector length squared. This is just the distance, the Pythagorean theorem in 3 dimensions. Distance formula. Alright, formula. Alright, so now let's take a look at, well, proof of property 2. Because, this is just a distance formula. How do you prove that? You can see the earlier videos on that. So proof of property 2 right here. So A dot B equals to B dot A. And again, this is a straightforward one. So if we write A vector dot B vector, again, write them in the components. Just for completeness, write them all out. A1, A2, A3 dot B1, B2, B3. This equals to, well, multiply these inside A1 times B1, just using the definition of the dot product. The next one's going to be A2 times B2, and then plus A3, B3, and then basically we could switch these around. You can move this back and forth. So in other words, just use the regular multiplication. properties, and you can just switch them around. These are just real numbers. So you can go 2 times 3 or 3 times 2. Those are always going to be 6. So we can switch these all around. So this equals to B1 A1 plus B2 A2 plus B3 A3. All right, and in other words, this is just the definition of a dot product for the vector in the front. So B1, B2, B3, those components. B1, this just equals to, I'll smooth put this equal sign there. This is going to be B1, A1, not A1, this is going to be B1, B2, B3 dot A1, A2, A3 dot, bracket like that. Yeah, so in other words, this is just the B vector dot A vector, like that. Put this down here, and scroll bracket. Alright, so now let's take a look at proof of property 3. This is one right here, A dot, and then B plus C equals A dot B plus A dot C, like that. Alright, so let's just write this out again using the definition. So proof of property 3, we're going to write A vector dot, and then it's going to be B plus C, and show that we can multiply that inside. So again, B plus C there. And we have to show that you can multiply this inside and FOIL it out. Alright, so A vector times or dot B plus C vectors, this equals to, in their component parts, A1, A2, A3, like that. And then the next one, B plus C, in their components, those are just adding vectors. And when you add vectors, you add each component. So this can be B1 plus C1, then B2 plus C2, and then B3 plus C3, like that. Alright, and now we can just apply the definition of the dot product. So multiply this A1 over here, and then each component's multiply and add it all up. So this equals to A1 times by B1 plus C1, and then plus A2, and then B2, we'll fix this up, A2, B2 plus C2, plus A3, B3 plus C3, like that. And just fixed this up like that. So that's what we have. And now what we could do is multiply this inside each one, just regular multiplication. So now we basically use a dot product, use a definition to get to the real numbers setup. And now we can apply the regular product rules. So A1 times B1. So what I'll do is I'll write A1 times B1 here, and then the A1 times C1 over here elsewhere. I'm going to write over here. A1 C1, and then we'll have this A2 B2 over here, and another one over at the side. This is going to be A2 B2, and then the next one A3 plus B3. Just so it's all together. Yeah, so we have those components first, plus, and now we'll do all these second terms, A1 plus C1. A1 plus C1 plus A2 times C2 plus A3 times C3. All right, and now this equals to, this is just the, I'll put a bracket like this. So this is just the dot product for the A times B vector, and this is dot product from A times C vector. So this just equals to A vector times B vector plus A vector dot C vector. And yeah, so hence we've proven our property like that. And yeah, so just scroll up here, and yeah, there's the property, we proved it. And now the next one, property 4, we'll look at C, the scalar C times A, and then dot product with B, and show that it equals these two. You could take the scalar out, or you can move it over to the B side, and so on. So that's property 4. All right, so let's write this down here. This is property 4. Again, that's the scalar C times A, and then dot product with B. All right, so we have C, A, and then dot product with B vector. This equals to, and write these in the components. This is scalar times it by, so we'll have this bracket like that, c times it by, and then the components of this vector a1, or just write it in the component form a2, a3, like that, and then dot components b1, b2, b3, like that. And now what we could do is, well, this scalar, we can multiply that inside as we showed in my earlier video, ca1, put this bracket like that, and then we'll have this ca2, and then ca3, and then just remove that out. Then b1, b2, b3. And now what we could do is, do the dot product definition. So c1 times a1 times b1. That becomes, well, ca1 b1, and then plus c a2 ca2 b2 plus c a3 b3, like that. And that's what we have there. Now we could factor out the c, and this just equals to c, and then a1 b1 plus a2 b2 plus a3 b3. And again, this is just basically this is just c times, this just becomes c times, well, this is the definition of the dot product for a times or a dot b vectors. So a dot b. In other words, we factor out the c out of there. That's what we have. That's proof of the middle part of the property. That's this one right here. So we show that it's a scalar times a dot b. And or instead of doing this one, we can multiply the c, or going over here. Yeah, or instead of here, this one here, I'll move the c inside here because these are all just real numbers. You can move the c over to inside there. So we could do or, I'll put an or sign, or this equals to a1 and then c b1. Just move those around, plus a2c, or a2c b2 plus a3c b3, like that. And this part right here, again, this is going backwards. This is the this part right here. Yeah, you could write it in this form, except the c becomes on this side here. So in other words, just for completeness, let's make it match this setup here. This just equals to the vector with components a1, a2, a3, and then this is gonna be dot c, I'll put the c, b1, c, b2, c, b3, etc., like that. And again, just for completeness, I'll just write this a1, a2, a3, dot, and factor out the c. And put a bracket here. So c bracket b1, b1, b2, b3, like that. And this just equals to a vector dot bracket c b vector, like that. All right, here. So we just proved this setup right there. And that is property 4. All right, now let's take a look at property 5, and that is just 0 vector dot b, and it show that it equals to 0. All right, so let's jump right here. So proof of property 5. This one's pretty straightforward. Again, a 0 vector dot by a vector. This just equals to the component of 0 vectors is 0, 0, 0 dot, and then we'll have a1, a2, a3, like that. In other words, just use the definition, 0 times every single one. 0 times a1 plus 0 times a2 plus 0 times a3. This just equals to 0. So real numbers. So 0 vector dot any vector just becomes 0. All right, so now that we've covered all the properties, let's continue further. So the dot product A dot B can be given a geometric interpretation in terms of the angle theta between A and B, which is defined to be the angle between the representations of A and B that start at the origin, where theta is between pi and 0, so it's greater than or equal to 0 and less than or equal to pi. In other words, 180 degrees. All right, so in other words, theta is the angle between the line segments OA, so from the origin to A, and OB in the figure below. So what we'll have is like this. All right, so let's draw this as the z-axis. This is the y-axis, and this is the x-axis. All right, it's the origin. And then this is going to be the b vector. We'll go to, so I'll draw this first. This is the A. So that's A. So we're going to A. And then, yeah, let's say that's the A. This is going to B. All right, so there's the OA. So this angle theta is there. And if this is, yeah, so this is going to A. Let's say the origin. This is the vector A. And this is the vector B. Remember, you have the vector there, A, and then the arrow's definition. This is just A minus B, like that. And yeah, here, if you add A plus A minus B, oh no, actually I have it, the arrow's the wrong way. So that's A. This is our A minus B, like that. And this is because when you have these vector, the way it's set up is, well, if you have B plus this vector, A minus B like that, this equals 2, well, this cancels, we're just left with A. Yeah. So that vector there going all the way over there is going to be A minus B. And here we will show that we can give this dot product a geometric interpretation using this setup, where that's the angle there between these two vectors, like that. All right, so let's continue further. And here's added this heading there. So geometric interpretation of the dot product, and also include that in the topics to cover later, or in the timestamp and so on. So note that if the vector A and B are parallel vectors, that is, they're all going across the same way, like that, then the angle theta is equal to 0, so both going in the same direction. But if it's if theta is equal to pi, both going in the opposite directions. Or in other words, read this probably. So if vectors A and B are parallel vectors, the angles theta is equal to 0, going in the same direction, or it's going in the reverse direction, and that is going to be our theta equals to pi, or 180 degrees, like that. I think it's going backwards and it's parallel, nonetheless. All right, so the formula in the following theorem is used by physicists as the definition, or quote definition, or it's an italicized word here, italicized definition, or a definition in italics, of the dot product. So this is typically how physicists define it. The definition 2, dot product. If the angle theta, or if theta, yeah, so if theta is the angle between the vectors A and B, like this, then this is defined as, a dot product is defined as A dot B equals to the distance A, or the length A, times it by the length B, times it by cosine theta. All right, so that's the definition there, but we'll show that this is actually equal to the dot product as we defined earlier. So proof here. So recall the law of cosines from here's a link from my earlier videos, the law of cosines, and you just find this random image online. So if you have a triangle, so has length sides A, B, and C, and then angles capital A, capital B, capital C, and so on, then you could plug in this formula for any of the 3 sides when you have one angle. So if you have this angle A, then you can determine, well, then A squared plus B squared plus C squared, no, A squared equals to B squared plus C squared minus 2BC cos A, and so on. And this applies for all of them. So for B, for the angle B, you're going to have a, yeah, this is going to be, so this is the b there. So you're going to have a squared plus c squared and then 2ac. And yeah, that's what this b squared is equal to. And likewise for the angle c here. So if you have c here, so c squared is this, and equals to d squared, and then minus 2ab, these two, and then there's a c. Like that. Anyway, so that's the law of cosine. So now if we apply the law of cosines, and again, I proved that in my earlier video. So now if we apply the law of cosines, yeah, to the triangle OAB in the earlier figure above, we get, so this one right here, so we have this angle theta, and then we have these lengths side there. There's this OAB set up there. So we could apply the law of cosines. We know this angle, so we're going to write this one squared, or I'll just write this as AB. Let's call that AB, that length or that distance there. Yeah, so I'll write it as AB. I'll write it out of vector form, just going to be the absolute value of the distance AB squared is equal to, so when you have that, then so if this is AB, for example, A, let's do this one here, you're going to have, this is going to be our A squared, is over here. Then these two sides squared, and then plus 2bc, etc. So in this case, we're going to have, so this one squared is equal to a squared, and then, yeah, so the length of a squared plus the length of b squared, or we'll call this OA and this OB. Like that. So it's going to be right here, OA squared plus OB squared. So those are the absolute values of the lengths there, those line segments. Then it's going to be minus 2. If this is AB, this is going to be 2A. Then this is going to be also OA, like that. And then this is going to be OB, like that. And then cosine theta. And again, we're just matching up this here. So if this is b squared, this is c squared, you're going to have 2bc, and there's going to be a negative sign. And then cosine that angle. All right, so that's what we have there. All right, so now that we have this, and before we go over the proof, I'm just going to look at these special cases here. Observe that the law of cosines that we wrote over here still applies in the limiting cases when theta equals 0 or pi, yeah, when equals 0 or pi, or a equals 0 or b equals 0. And I'm not going to go through all of them, and they're pretty straightforward because we're going to prove it anyways. And more rigidly, this one's just more graphically. For example, we're just going to look at this case right here. So when theta equals 0, so if you look at how this set up here, this angle's 0, then this vector b goes down. It's going to be parallel with a and in the same direction there. So for example, we're going to have, I'm just going to write a straight line like this, because all we care about is the vector direction. So we just care about this one here. We're going to make everything relative to this OA there. So this is O, this is A. Now the B is flattened, so the angle's this angle's 0. So theta is equal to 0. This distance right here, and this is the up to B. And now the distance between these ones is going to be our AB, the absolute value there. And this distance here, let's put this angle like that. And now this distance here to here, this is OB. And now the full length is just OA. So in other words, if we want to find out AB squared, this equals to, well, we could have put a bracket. This is going to be OA minus OB. So absolute value of OA minus absolute value of OB. Like that. Then this is all squared. Now if you FOIL this out, we'll just put this for completeness. OA absolute value, OB absolute value, and then OA minus, again, OB. Like that, and then FOIL it out. FOIL, 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 FOIL. This equals 2. This is going to be OA squared. And then inside here is going to be negative 2, because you're going to have this one times by this, then this times this. You're going to have OA times OB. And then we're going to do the same thing, OB times OA. We're going to have 2 OA times OB. Like that. And finally, this one multiplied by this, negatives cancel, becomes plus OB squared. So again, this is basic foiling out. All right, so that's what we have there. That's what our AB squared is. And now if we look at this setup here, this one here is, this is when cosine is 0, this becomes 1. And in other words, this is matches. So you can see here, OA squared, then you have the OB squared, then you have a negative 2OB there. So in other words, this is correct, like that. And I'll put, yeah, so in other words, I'll put in bracket cosine theta equals, cosine 0 equals to 1. So anyways, we just proved this is correct even when you have theta is equal to 0 and it's just lines parallel. So it's very, very fascinating. All right, and yeah, these other cases where theta equals pi or these a equals 0 or b equals 0 vector, etc., those you could work on those yourself. It's pretty much, it could be very, very similar to this setup here. Just do it algebraically. Graphically and then algebraically. So anyways, let's go back to here. So since OA equals to, well, the length of this A vector, and OB is just this B vector, so we're going to write this all in vector form. And then AB here is just going to be A minus B, like that. Yeah, or the length of the A minus B. Yeah, so here, so OA, the absolute value, the line segment is equal to the length of the A vector. OB is the length of the B vector, and then AB is the length of the A minus B vector. The above equation, this one here becomes, and this becomes A vector minus B vector squared is equal to, and the OA becomes A vector, this one's B squared, and this one's going to be negative 2AB cosine theta. This can be A vector squared plus B vector squared minus 2, and this can be A vector length, and not squared, and then the next one's going to be B, like that, length, and then cosine theta, like that. All right, so now that we have this set up here, and now what we're going to do is, well, we're going to use properties 1, 2, and 3 of the dot product, or using it, we can rewrite the left side, so this part right here, of this equation as follows. So let's just recall our properties. So we have property, this one here, A dot A is equal to, well, this length A squared. And this one, the next one, you could rearrange these sides, and then this is the foiling one out is property 3. So let's take a look at it here. We're gonna try to rewrite this part right here. So let's try this. A vector minus B vector squared, or the length of it all squared, and then it's gonna be equal to A minus B squared. So length, magnitude, whatever you want to call it, distance, and just write this as A minus B, like that. Yeah, in other words, we're just going to be foiling this all out, but I'm going to go step by step just so we match the properties as listed here, and just do it just slowly and methodically. So we're going to do, yeah, this property here, and then later we're going to do the reverse one, and then also this one right here later. Let's just do this slowly. Let's do grasp it. So what I'll do is, yeah, so multiply this A minus B times by A, and or dot product it, so A minus B dot A dot, like that, and then minus, and now this times it by the B one, thus becomes A minus B, like that, vector dot B vector, and then multiply this now inside here, etc., this inside here. And this side. Again, this is just basic foiling. I just wanted to do that step by step, but later you could just do foiling. This times this, exactly like real numbers. So you just do that, and so on. And we're gonna get is A squared. This is A. Yeah, A times this one here, A dot A. And then we're gonna have minus A dot B. Yeah, minus A. Yeah, so we're gonna have it here. Well, I'll just write this as just as it is, and we'll do the property 2 later. A B dot A, and then the next one here, this one, multiply inside, and so on. So what we get is minus A dot B, and then this minus becomes a positive, plus b dot, b dot. I mean, b dot b. All right, and again, this is exactly as we expected. So this is going to be, now this is property 1. This just equals to the length squared. The next one here, we can just add, this one we can just rearrange. This becomes AB using property 2. And then add these up. This becomes 2AB, like that. AB, and the next one here is plus this one right here using the property 1. B, length of the B or magnitude and then squared, like that. That is fascinating stuff here. We could box this in. We'll box this all in. Like that. Like this. Alright, so now thus, putting the two equations together, we have this is the left side, and now we have this cosine law set up there. To put them together, we have, or I'll just put it all for completeness first. So so A minus B vectors squared equals to, using the cosine law setup, A vector, the magnitude squared plus B squared minus 2A B magnitude cosine theta. So that's this setup right here. And now we have this one right here. So we have this, and we have this. And equate them. Let's put those together. And I'll do that right here. So this equals to, and yes, write this all down here. So A squared minus 2AB squared plus B squared, like that. And now this equals to this. And I'm going to do here, I'm going to copy this. Copy and paste. Whoops. I'm going to copy this. I'm going to paste it here, save time, and move this all the way across here. Alright, so that equals to that, and now we can just do some simplification. Well, this cancels, this cancels. This cancels, this cancels. And what we're left with is, well, this and this. So in other words, we get negative 2A, the A and B, this is a dot number, there's a dot product there. So A dot B equals to negative 2, absolute value of A, or the magnitude vector A, magnitude vector B, cosine theta, like that. Alright, so as we have negative, those are negatives. And the negatives cancel, of course. And what do you know? We have A dot B dot equals to the magnitude A times by magnitude B cosine theta. Absolutely magical. Yeah, so in other words, we prove that a dot product is equal to, well, this geometric view with a cosine angle there, and is also equal to our earlier definition. And yeah, so it's pretty fascinating. And we just started with the cosine law, and then also this squaring using the dot product properties and so on. So it's very, very fascinating. So now let's go take a look at example 2. So if the vectors A and B have lengths 4 and 6, and the angle between them is pi/3, find A dot B. All right, so solution. Using the alternative definition of the dot product, in other words, definition 2, the physics definition, we have, so again, we are asked to find A dot B. So we know that, well, A dot B is equal to, and all we're given is lengths and the angle. We don't have the actual components. What we could do, though, is, well, we know it's this. So we know that is the definition. So we could go the length A of the length times by length B cosine theta. In other words, in this case, we're going to have lengths 4 times 6 times by cosine pi/3. Like that. And then the question is, well, what is pi/3? And if you recall from my earlier videos, or just recall trig identities, and the way I do it for this pi/3, that's just 60 degrees, because number pi is 180 divided by 3, 60. So what I'll do is I'm going to draw a equilateral triangle like this. All the sides are length 2, 2, And this one, I'm going to split this in half so that this length is 1, 1. So there's all 2. So in other words, all these angles are going to be, a good way of memorizing it, pi over 3. It's going to be pi over 3. So all of them are 60 degrees. And then this one here is splitting in half. So it's going to be pi over 6. Pi over 6. And we're looking at cosine of pi over 3. In other words, cosine is adjacent of our hypotenuse. Cosine pi over 3 is just equal to, well, 1 over 2. 1 over 2, like that. So in other words, this equals 2. Put that over top. Just put the end of this little recall thingy. Let's put a line. Equals to 4 times 6 is 24. Or actually, before I even get to that, I will just do, actually, I'll just leave it like that. So 4 times 6 times it by 1/2. This is 2. This cancels. And we're left with 2 times 6 is 12. So in other words, the dot product is 12. Which is quite fascinating. Alright, so now let's continue further. So the alternative dot product formula, or definition 2, allows us to find the angle between two vectors. So if we have the length and the dot product, we can just find the angle. So corollary. In other words, this is the theorem that follows from another one. So if theta is the angle between the non-zero vectors a and b, then, and we could just rearrange this formula here, cosine, remove these, or just move these across here to the other side. So we're just left with the cosine. So what we get is, well, cosine theta. Let's write this neater. Cosine theta is equal to a vector dot b vector over a vector, the lengths a, b, like that. So just move those over to the other side. So that's very fascinating stuff there. All right, so now that we have this corollary, let's go over example 3. So example 3 states, find the angle between vectors, or between the vectors, a, which has components 2, 2, and -1, and b, which has components 5, -3, and 2. And let's take a look at the solution now. All right, so we're basically finding the angle between these two vectors. So solution, let's solve all the terms of the corollary formula, because we're going to need the angle there. So we have to do the dot product, and then we have to do the lengths there. So let's just do, the lengths first. Again, the length is just 3D trigonometric formula, or the distance formula. So let's get the lengths here. So the length of A is equal to, well, the positive square root of, and this is going to be, well, this is, I'll write this here and just skip it. Yeah, this is going to be 2 squared. So square root of all this plus 2 squared, all the components squared, plus -1 squared. -1 squared. This equals 2, like this. Just, so this equals to, so 2 squared is going to be equals to 4 plus 4, and then this one's going to be plus 1. So 8 plus 1 is 9. So that's going to be 9. Yeah, equals square root 9 equals to 3. All right, that's that one. And then the length of the B is equal to, like this. It's going to be 5, -3, 2. 5 squared plus -3 squared plus 2 squared. This equals to 25 plus -3 squared is going to be, well, 9. Negatives cancel. Plus 4, like that. All right, so what this is equal to, well, 25 plus 4 is 29, or actually, let's go here. 25 plus 10 is 35, so -1, so 34. Then 34 plus 4 is equal to square root 38, and we're not going to solve that, just leave it like that. All right, so we have the lengths, and now let's look at the dot product there, A dot B. So A dot B is equal to all the components. So 2 times 2, let's put this all for completeness. 2, 2, -1, dot, 5, -3, and then 2 like that. And then this equals 2. Well, this is going to be multiply this, and then, yeah, it's multiply all the components. this equals 2, and it's going to be a real number, so we don't need to have the bracket. So 2 times 5 plus 2 negative 3, and then plus negative 1 times by 2. And this equals 2, well, that's going to be 10. 2 times 5 is 10. And then 2 times negative 3 is 6, negative 6. And then negative 1 times 2 is negative 2. This equals 2, well, negative 8. And this becomes, this is negative 8. So 10 minus 8 is equal to 2. Like that. All right, so the angle between A and B is, and we just plug in our corollary formula, cosine theta. So cosine theta equals 2, let's put a completeness, write this down. The dot product A dot B divided by length A, length B. Like that, and this equals 2, well, dot product is 2. And then divided by 3 is the length of the A, and then square root 13. 3, then square root, 38. Like that. Alright, so that's the cosine, and we just take the inverse. So theta is equal to A tangent, arc cosine or A cosine, or cosine inverse, like that. And 2, and then 3, 38, like that. If you plug this into the calculator, what you end up getting is, this is going to be roughly equal to 1.46 radians. And, or I'll box this just for completeness, or in degrees, this is equal to, this is going to be, or it's going to be 84 degrees. Or 84 degrees. And now let's do a quick calculation check. So my OneNote, the OneNote program that I'm using has a built-in calculator. So if you write A cosine, so A cos, and then bracket 2 divided by 3, then you can write squared, or SQRT for square root 38, put the corresponding correct brackets. Delete this. The thing is, default is in degrees, like that. And you get 83.79 instead of rounded up to 84. And then if you plug that inside here, times it by pi divided by 180, because pi radians for every 180 degrees, and then you get erase and press space, and you get 1.462, etc. Just fascinating stuff. All right, so now let's continue further and now look at perpendicular vectors. So, and yeah, here this heading, I'll put this in the topics to cover. I just added this right now. So anyways, two non-zero vectors A and B are perpendicular or orthogonal. Again, basically the 90 degrees setup like that. If the angle between them is theta equals to pi over 2 radians, or 90 degrees. Then the alternative dot product formula becomes, or definition 2, this just becomes A dot B for the angles. For the angle theta is equal to pi over 2. This is equals to, like this, A, like that. Yes, this becomes, and then the cosine pi over 2. In other words, this becomes, well, this is 0 actually. So this equals to 0. And we'll illustrate this later. This is cosine pi over 2. And yeah, I'll graph this out later for cosine just to recall it later. But yeah, so cosine pi over 2 is 0. So this whole thing vanishes. And that's when it's orthogonal or perpendicular, when the non-zero vectors A and B are perpendicular. And conversely, if the dot product A dot B is equal to 0, then cosine theta is also going to equal to 0. And hence cosine, yeah, so this cosine right here. So this dot product is 0. Then this one has to be 0 too if these ones are non-zero. So then you have the cosine is going to be 0. So then the angle is going to be theta is equal to pi over 2. And yeah, so the 0 vector, this right here, 0 vector, is considered to be perpendicular to all vectors. So yes, very interesting. So 0 vector is always perpendicular, just by definition. Therefore, we have the following method for determining whether two vectors are orthogonal. Two vectors A and B are orthogonal or perpendicular if and only if the dot product is equal to 0. Absolutely, yeah, fascinating stuff there. And now let's take a look at example 4. And this one states, show that if 2i, this is the standard basis vector, 2i vector plus 2j minus k is perpendicular to 5i minus 4j plus 2k. So show that this is perpendicular. So solution, determining the dot product, is all we got to do is determine dot product. If it's 0, then it's perpendicular. All right, let's take a look at this dot product. All right, so we get, I'm just going to write this like this, 2, put as regular brackets, the vectors are already inside, plus 2i plus 2j minus k vectors placed on top, and then dot 5i vector minus 4j vector plus 2k vector, like this. And then, yeah, do the dot product, all the component parts here. I'm going to write this, actually, I'm going to write this, move it to the left. Okay, so move it over there. This equals 2, and I'm going to put it over. Let's put it, where should we put it? Right here. See. All right. And then this is 2 times 5. Yeah, this is just going to be 2 times 5. Plus, yeah, 2 times negative 4. And then plus negative 1. And then 2. Like that. This equals to 10 minus 8 minus 2. And yeah, that's just 10, so this equals to 0. Yeah, so it is orthogonal. Or perpendicular. Write a better box. Perfect. Alright, yeah, so finish off example 4. So thus, these vectors are perpendicular by the earlier theorem. That's fascinating. And now here's another section. I just added the heading on this one here. So vector angle. So because cosine theta is greater than 0 if the angle theta is between 0 and pi over 2, and cosine theta is less than 0 if theta is less than pi over 2 and less than or equal to pi, we see that A dot B is positive. Yeah, it's positive for theta is less than pi over 2 and negative for theta is greater than pi over 2. And here's, I'll just graph it, all the components of it. So let's say we have this angle theta is the x-axis. Now we have the cosine theta as the y-axis. I'll just put a y like that. All right, so now we have, I'll do this a bit better. All right, so that is pretty decent actually. All right, that's pretty good. All right, here I just fixed it up. So basically, here's the cosine theta graph like this. And this is at pi over 2, just recall it. And here's at pi, like that. And notice here, because we're only considering from 0 to pi, from 0 to 180 degrees. So then this is positive. And then I'll put this on top. Pi. And then over here, this is negative. So because cosine theta is greater than 0, if theta is between here, and cosine theta is less than 0 if it's between here, we see that A dot B is positive for angles less than pi over 2, and negative for theta is greater than 2. So the cosine theta is going to be, or the dot product will be positive or negative, because it is dependent on the cosine of the theta of the angle. So there's dot product and it's dependent on it. Yeah, so it depends on the angle. It could be negative or positive. All right, going further, we can think of the dot product A dot B as measuring the extent to which A and B vectors point in the same general direction. So it's 0 if they are perpendicular and negative if they point in generally opposite directions, as illustrated below. All right, so for example, let's say you had vectors A like this. This is A. And you had a vector B like this, and this is theta. Let's put theta in between here. All right, here, just fix that up. So this is our B vector. There's our angle between them is theta. So this is a small angle. This one here, A dot B, would be greater than 0 because this angle is between here. So this angle is between there, so it's less than 90 degrees. And in other words, theta is acute, like that, or less than pi over 2. Less than pi over 2, like that. And then if it equals to pi over 2, then that's going to be a 0 dot product, and it's going to be perpendicular, like this and this. This is perpendicular. This is going to be our B vector. It's our A vector. And this our angle is going to be, well, yeah, this angle right here is 90 degrees. So A dot B equals to 0, and theta equals to pi over 2, or 90 degrees, so pi over 2 radians. And then finally here, because we show that it's negative for the angles greater than pi over 2, in other words, if it is obtuse, so greater than 90 degrees, so let's say you had angle A, and then this is angle B, vector B, and there's the angle theta, like that, and that's very large, so we'll have A dot B vector is greater, it's going to be less than 0, it's going to be negative. So this is, this theta is obtuse. In other words, we'll have it as greater than pi over 2. Like that's so very, very fascinating stuff here. All right, and going further, so in the extreme case where A and B point in exactly the same direction, we have the angle theta is equal to 0, so cosine theta is equal to 1, because remember this is just 1 there. So when it's 0, it gets 1, and then also when it's pi, it becomes negative 1, just for reference, because we'll include this here soon. And this is like this is a negative 1, like that. So the cosine theta is equal to 1. In other words, a dot product, let's go to that theorem right here. This becomes 1. This is equals to A dot B equals 2 right here. Equals to lengths times each other. So in other words, we'll have A dot B is equal to the lengths multiplied by each other. And yeah, so that's it. Because cosine 0 is equal to, yeah, this just goes to 1. Yeah, so I'll just leave it like that because we just wrote it. All right, so that's what we have. That's fascinating stuff. All right, and lastly, if A and B point in exactly opposite directions, then the angle theta is equal to pi, so cosine theta is equal to negative 1, and A dot B is going to equal to negative, a negative length A times length B. Yes, very fascinating. All right, so now let's go to the next section. That's on direction angles and direction cosines. So the direction angles of a non-zero vector A are the angles alpha, beta, and gamma in the, this is in the, again, the domain from 0 to pi, or in the interval from 0 to pi, and this is closed, yeah, this is closed bracket, so it includes them. And yeah, and this is the direction angles that A makes with the positive x, y, and z axis. See the figure below. So now we're looking at, yeah, 3-dimensional and have all of these yeah, angles. These are the considered unit angles or whatnot, and this is based on the axis of the coordinate system. So yeah, for example, if you, let's just graph this out in 3D. So we have, here we have, this is our z axis. Let's draw our y-axis, and then this is our x-axis, like that. All right, so as we have, and let's say we have a vector goes out here in 3D space like that, and we're gonna do, what I'm gonna do is, yeah, is just draw the components of this. I'm gonna draw this 3D, I'm gonna dash lines across down here. So it goes down like that, and then it goes like this. All right, well, let's fix that up. And I'm gonna draw it across here, perpendicular across there. And likewise for the vertical side, goes like that, high part, goes all the way down. So we draw a 3D rectangle, show it in 3D space. And put this up as well. And then down here. And then down here, this across there. And let's fix it up like that. And all right, so we drew this. There's the vector A. I just fixed the box up like that. All right, so now let's draw the angle. So this is the angles. Alpha is going to go from the x-axis to this angle. To this vector. It's going to look like this. This is the alpha. And then the y1 is the beta. It's going from the y-axis. That's beta. Like that. And then the z-axis is the gamma going over to here. And this one is gamma. Like that. Very fascinating stuff. And I'm also going to draw a line here. This segment is a component because we're going to use this. I'm going to point this out later. Put this a bit better. This is A1. Like that distance A1, and corresponding here is A2, and then the vertical is A3, and so on. All right, now what we have here is something very interesting, because if we take the cosines of every single one, notice we'll have the adjacent of every single one, and the hypotenuse is the length of this vector A. So if we take the cosines of every single one, yeah, the cosines of these direction angles, cosine alpha, cosine beta, cosine gamma, are called the direction cosines of the vector A, and those are just going to be the components of it. Well, cosine times it by the length across it. So using the earlier corollary with b replaced by I, which is the x vector there, or just a unit vector in a direction of x-axis, we obtain, and then the corollary is just the cosine set up here. Let's go back here. That's just this one right here. We're going to replace b with I. So cosine theta equals to a dot b. Instead of that, we'll do dot I. All right, so let's write this down. So cosine alpha. So we're going to replace that out, and we're going to write cosine alpha instead of cosine theta. And we're going to do cosine alpha here is equal to, and then we're going to use the I, this part right here. It's going to be the I vector. I'll just put this here. The A vector dot the I vector. And then this is going to be divided by A, and then divided by B length. I mean, divided by the A length, and then the B, and then the I length. All right. All right, here I just fix it all up. So A dot I divided by A length, and then the I length. And again, the I is, this is the I. Like that. It's just over there. The I is there. This is the J. And this is the Z, etc. I mean, this is the K. K is going top, etc. And I'm just going to erase all these just for neatness. All right. Yeah, although, however, it is important to include this I there. This is going to be the I unit vector, or the I standard basis vector, like that. So that's the I there, and its length is 1. All right, now before I solve this or simplify it, I'm going to do a recall. Again, recall from an earlier video what this all means. The unit vector, or the standard basis vector I. So I dot, this just equals to 1, 0, 0, like that. This here is 0, 0. Yeah, so that's just how its components of this vector. And the length of it is just a unit 1, it's just 1. Is equal to 1, like that. So we have that and that. Thus, A dot I, or I'll just recall that. Put it like that. Thus, I'll just leave that line out of there. All right, so thus A dot I is equal to, well, A1, A2, A3 dot 1, 0, 0. This all equals to, well, the A1's times by 1 times by 1, plus the next one's going to be, well, 0 times A2 times 0, and so on. So in other words, it's going to be 0 plus 0. This all equals to a1. Like that. Yeah, so in other words, this equals to 1, and then the a dot I is equal to a1. So this equals to a1 over a1, the length a. Like that. Where a1, again, is here. That's why I wrote it down there. There's a1. And there's this is actually some pretty fascinating stuff. Once you grasp it, because then you can move this a1 over to here. So this is just going to be cosine of this alpha times by the length is equal to a1. So that's just the direction cosines. Fascinating stuff. And as I just stated, this can also be seen directly from the earlier figure. So if this is the angle, if that's the component there, then this triangle like that, you draw this triangle all the way across there. Let's make this fit like that. If you draw it all the way across there, what you end up getting is you'll have something like this. I'll just draw it only without that component. I'll make that flat setup like this. And as this is a1, this angle is going to be our alpha. This length is going to be a1 like that. And yeah, this is a bit skewed, but yeah, that is the right angle there, because it's notice how we have this going across from here to here, all the way to across there. This is going to be a perfect right angle across there, but tilted upwards, which is quite fascinating. So we got rid of that. So that's right angle, and that is that's just basic trigonometry, and cosine theta is equal to adjacent over hypotenuse over a1 length, like that. Yes, which is quite fascinating. All right, and similarly, if we do the same thing for the other ones, we use, instead of I, we use J, we use K, etc. Because remember, this one's going to be 1, 0, 0, J is going to be 0, 1, 0, K is going to be 0, 0, 1, and you're basically just going to be using a different angle, but it's going to be exactly the same setup. So similarly, we also have for the y component cosine beta is equal to a2 over the length of the a vector, and cosine gamma is going to equal to a3 component, because then everything else cancels when you're multiplying by the k vector, but the last one there. So a3, and this is going to be vector like that. Alright, so now going further, by squaring the above direction cosines, we see that, I mean squaring and adding. So squaring and adding the above direction cosines, we see that, well, if we take every single one, cosine alpha, cosine squared alpha, or cosine alpha squared, plus cosine squared of the beta 1, plus cosine squared of the gamma, this equals to, well, notice every single one has this 1 divided by the length a, then you have this a1, a2, etc. So this just equals to 1 over, and we're going to be squaring it all. Well, might as well for completeness just write it all together. So a1 over, this is going to be a like that, squared. So we're squaring it, squared, squared, and then plus a2 squared squared plus a3 squared, like that. Factor it out like this. Now we're going to get a1 squared plus a2 squared plus a3 squared. And this one right here, this is equals to, again, that's just the three-dimensional trigonometric function. That's just going to be a squared. In other words, this whole thing cancels. And this cancels this. So this is equals to 1. So this equals to 1. In other words, just down here, cosine squared alpha plus cosine squared beta plus cosine squared gamma equals to pi a equals to 1. Like that. Alright, going further, we can also use the direction cosines to write, and let's just write our vector A with its components a1, a2, a3. This equals 2, and then we could write these all out. Using the a1 number, a1 is just going to be the length a times by the cosine of the alpha. And then cosine, and then the next one is a alpha, the length a multiplied by cosine beta, and then length a multiplied by the cosine gamma, like that. Alright, let's move that over, and now we just factor out the length a, like that, cosine alpha, and then cosine beta, cosine gamma. It's quite fascinating. And now just factor out this whole thing out, move it over. So in other words, move it all the way to the other side. So what we get is thus we have 1 over the length times it by the length of the a vector times by the a vector is equal to cosine, equal to direction cosines. Cosine alpha. And then we have cosine, that's cosine alpha, cosine beta, put a better B, cosine gamma. Put this better B, like that, or better beta. Alright, so now let's just box this whole thing in. Yes, fascinating stuff. And now what this equation says is that the direction cosines of A are the components of the unit vector in the direction of A, which is quite fascinating. This is a unit vector. Basically, so if you have length A, if you have vector A, if you look at the length of it, it's going to be this. But then this is just a scalar number, so you're dividing by it. So it's going to equal to 1. So it's going to be length 1, and it's going to be the direction of A. So if you have A like this, it's going to go in the unit vector here. It's going to be length 1 of the components there, and all these cosines are going to be all of the ratios of that rectangle box, etc. As before. Yeah, here's drew a better rectangle box, but anyways, it's just the x, y, z components, or I, J, K components of it. Serious, fascinating stuff. So going further, let's take a look at example 5, and this one states, find the direction angles of the vector A, which has components 1, 2, and 3. Alright, so now if we were to solve this, well, we know that the direction angle, or the direction cosines, if you just go back above here, it's just going to be A1 over the length A, or A2 over length A, or A3 over length A. So find the angle, but we're never asked to find the angles of it. So first we need to get the length first. Length A is going to equal to square root 1 squared, all the components squared, plus 2 squared plus 3 squared. This equals to 1 plus 4 plus 9. In other words, 9 plus 1 is, 9 plus 1 is 10, plus 4 is 14. The square root of 14. Thus, let's get all the direction cosines first, and then we'll do the angles after. So let's get the cosines. Cosine alpha is equal to, again, that's just Greek letter alpha, A1 over the length A, like that. This equals to 1 over square root 14. Cosine beta, this equals to A2 over the length A. This equals to 2 over 14. Because again, that's component's 2, then the next one's going to be 3. And then cosine gamma, this equals to A3 over unit vector, the length A equals to 3 over 14. Alright, so that's what we have here. So now, instead of saying thus, let's write so. We already had it thus, I'll just say so. Or so we get, now we just take the inverse, so alpha is equal to inverse cosine, or arc cosine, or a cosine, 1 over 14. 1 over square root 14. And now if you plug this into the calculator, you should get around 74 degrees. I'll box this out because that's what we're asked to find. We're asked to find all of the angles, find the angles of this vector. So 74 degrees, and then the next one is beta is equal to cosine inverse 2 over square root 14. And this equals to, plug in the calculator, you get 58 degrees. It's quite interesting. All right, so that's 58. All right, the next one now is the gamma. This equals to cosine 3 over square root 14. Let's write this a bit neater. Like this. This equals to, plug in the calculator, 37 degrees. Like that. And now we'll do a quick calculation check as per usual. Again, this is built-in one-note calculator. Put a cos or arc cosine or inverse cosine 1 divided by square root 14 or sqrt 14, and then press space, auto calculates, which is quite fascinating. And 74.49, etc. rounds down to 74. The next one, 57.68. That's right, rounds up to 58. Next one, 36. Again, this is 1, 2, 3. 36 rounds up to 37, yeah, 36.699, etc. Yes, quite fascinating. All right, so now let's take a look at projections, the next section. So the figure below shows PQ and PR of two vectors A and B with the same initial point. So let's say we have here these two line segments here. So we have the same starting points. Let's say it's starting at P. And it goes over to, you have PQ. Let's say it goes to PQ like this. This is Q. And it has PR, goes to here, like that. That's PR, this is PQ. All right, yeah, just fix that up. And this is the vectors A, and this is the vector B. All right, so if S is the foot of the perpendicular line from R to the line PQ, so that would be all the way here, and then you draw a perpendicular line, like this dot, and then there is a perpendicular line. Then that is S, is the foot of it. Then the vector with representation PS is called the vector projection of B, yeah, onto A, and is denoted by then this subscript A and then B, or projection A and B. And just note here, it says PS is, so PS is vector. I'm going to draw this in red, like that. So that is this PS vector. And yeah, it's denoted by this projection subscript A and then B vector. And you can think of it as a shadow of B. So it's shadow of it onto this setup right here. And this arrow right here, this is projection of A, and it's bold, but it's a bit small. Then put the B on top like that. You know, right here I just fixed that up, and this is an angle that is that's less than 90 degrees. Let's draw one that's more. So what happens is, if you had one like this, let's say same starting point, you go from P over here. Let's say that's Q. So this is P. Now you have a vector A. And then you have the vector B like this. And then going to R, this is B, like that. And then going across, this way is going to be our S setup here. And this is this projection goes all the way down here, and it's 90 degrees. Like that. Yeah, so that's going, the shadow of it goes down, or the projection goes down here, so it's perpendicular. And then we'll have it going backwards now, this S set up there. And this would be the S here. And here I'll write S, and then this right here is our projection, the same setup there, but different angle. projection. Let's write this nicer. A bit hard writing it. Subscript A and then B subscript. No, I mean arrow on top. So subscript A with arrow on top and then B arrow on top and so on. So yes, fascinating stuff. All right, here I just moved it over to this side by side, so a bit neater. All right, so let's go further now. The scalar projections. This was a vector projection. We're projecting the vector onto here, and we have this projection there, like that. So the scalar projection of B onto A, also called the component of B along A, is defined to be the signed magnitude of the vector projection. So the actual magnitude of it, which is the number. Yeah, the number which is length B cosine theta, where theta is the angle between A and B, and see the figure below. And this is denoted by this comp or component, and then subscript A vector, and then a B vector, like that. So let's draw this out. And so if you have again similar to the above one, so you have the P, and it goes to Q. This is our A vector. Now you have the R like that. This is the R. This is the B like that. And then this goes all the way across like this. And this is our right angle. This is our S. And now the magnitude of this vector projection is going to be, well, this is an angle theta. So this right here. Yeah, this right here, I'm going to draw this in red. So this right here is the magnitude of it. And it's a signed magnitude, so it could be negative or positive and so on. So what we'll have here now is this is right here. I'll put it like this. I'll put it like this. And this is the length of the B. So that's the hypotenuse, and there's just going to be cosine again, like always. Cosine theta, and you can write this as comp, is denoted by comp subscript A of the vector B. So the component of B along A. Yes, fascinating stuff. Yes, and since this is the signed magnitude, because notice it's a cosine theta, so observe that the component AB is negative if this angle right here, theta, is between pi over 2 and pi. So if it's greater than pi over 2, it's going to be negative. Yeah, so it's going to be negative there. And if it equals to pi, it's going to be negative 1 there. So yes, it's going to be a negative angle there. So it's interesting. And now note that the equation, so if we write this out, the dot product, A dot B, this equals to, well, the lengths A times by the length B of cosine theta. And we know that the component of B along A, or the component of B along A, or the scalar projection of B onto A, is just this B, length B times cosine theta. In other words, we could write this as like this, and then put a bracket. So this is the component. Like this. In other words, this equals to the length of A times it by the component of B along A, or the scalar projection of B onto A, or of B onto A. Yes, fascinating stuff. Yeah, so this equation right here shows that the dot product of A and B can be interpreted as the length of A times the scalar projection of B onto A, which is quite interesting. So if you look at it here, this could be viewed as the length of A times by the projection of B onto A. So which is so you're multiplying it the amount that's actually the shadow is actually hitting here, perpendicular, so which is quite interesting. All right, so now going further, since we have this right here, the length of B cosine theta is equal to, and here what I've done here is just move this over to this side, and so all we're left with is the component of B onto A. So what we get is this dot product, A dot B over the length A, like that. And then in a unit vector form, just write these together. This can be A over length A dot B, like that. So the component, or the component of B, or the scalar projection of B onto A, is going to be the unit vector of A dot product with B. It's quite interesting. Yeah, so here I've written it down. So since we have this, then the component of B along A, yes, the component of B along A can be computed by taking the dot product of B with the unit vector in the direction of A. So there's a unit vector in the direction of A there, because that's the number, that's the length of 1, because you're dividing by the full length there. So we summarize these ideas as follows. So summary of projections. All right, so the first one is scalar projection of B onto A. That's just this comp setup over here. In other words, comp, I'll write this here, comp of, this is going to be B along A, the subscript A, is equal to, and that is just here, move this over A to this other side. So dot product divided by the length. So dot product of A dot B divided by the length of A, like this. All right, so that's the scalar projection. And now let's look at the vector projection of B onto A. So the projection proj like that, subscript A of B. So B is projection of B onto A in vector format. Yeah, this equals 2. So scroll back to our projections. Yeah, this projection, so that's a vector format. So basically, we need to know the direction of this. Yeah, so the direction of this projection of B onto A. And we know the magnitude of it. That's the full size. It's assigned size, and that whether it's negative or positive will determine the direction. So in other words, we could write this as projection of B onto A is equal to the component of B onto A. I'll just write this. Yeah, so that's equals to this part right here, and write this as A dot B over the length A, and then multiply this by, well, the unit vector in the direction of A, like that. So it's gonna be the direction of A there, because that's where the component is, and this sign is whether it's negative or positive depending on the angle of the vector B relative to A. So yes, that's fascinating. So in other words, this right here, I'll put this. This is the component onto A of B, and this right here is the unit vector. This is a unit vector along the direction of A. So yes, fascinating stuff. All right, let's continue further. All right, so now continue further. So notice again, as I stated here, notice that the vector projection is just a scalar projection times or multiplied the unit multiplied by the unit vector in the direction of A. So that's the unit vector in the direction of A, hence this vector, and there's the length of it. All right, very interesting. So now let's continue further and look at example 6. And this one states, find the scalar projection and vector projection of the vector B with components 1, 1, 2 onto A, which has components negative 2, 3, and 1. All right, so let's get the scalar, which is the component one, and then we'll do the vector projection because we multiply the unit vector. So let's take a look at this. So component onto A of B. So B onto A. Oops. Let's erase this better. Component. This right here, this equals 2, and this is just, again, the vector and the dot product divided by the length. So this is going to be A dot B over length A. This equals 2, and let's put this all together. So the dot product will have this 1 times negative 1, or we'll go A here first. So negative 2 times by 1 plus 3 times 1 plus 1 times 2. and then divided by, and now we're going to look at the length of A here. That's going to be square root, the positive square root, negative 2 squared plus 3 squared plus 1 squared, which equals 2. This equals to, well, negative 2 plus 3 plus 2. This cancels. We're left with 3. And then the bottom's going to be 4 plus 9 plus 1. That's just square root 14 because it's 4 plus 1 is 5, or 9 plus 1 is 10. Yeah, that's just 10 right here. And then 4 plus 10 is 14. So this equals to 3 over, or I'll just move it over here, move everything over there, fit it all in there. So 3 over square root 14 is the component of B, the magnitude of the projection onto it. Now we just got to multiply by the unit vector along A, and we'll do that here. So the vector projection is this scalar projection of here times the unit vector in the direction of A. So let's write it down. Projection of unit vector, of B onto A is equal to the component, or the scalar projection. This is along A of B along A multiplied by, this is going to be the A vector, the unit vector along A. In other words, divide this by its length. So this all equals 2, and let's put it all together here. So put it on top there, and we know that this is just 3 over square root 14 is the component. And then multiply by A. Well, let's plug in A as the vectors. Here's negative 2, 3, and 1. Negative 2, 3, and 1. And the length is, we know A is 14. Like that. And yeah, notice there's going to be a square there. And actually, here, this part, you can simplify this further. Actually, I forgot to do this. This is just going to be A dot B over A squared, and then A dot. A like that. So dot product there, and then yeah, multiply it all that. It's unit vector, and when we get end up this one here, when we simplify this right here, so this A squared, this length A times by length A, that's gonna be length A squared. That's fascinating stuff. And then there's the dot product. All right, continue further. All right, so we have this part right here, and now what we're gonna do is I'm gonna multiply these out. So yeah, just squaring that, the square roots cancel. Square root 14 times square root 14, the square roots cancel. And we're just going to be left with 3 over 14. And then we're going to have this, this is the A vector. Negative 2, 3, 1, like that. All right, and now what we'll do is multiply this inside. 3 times negative 2 is going to be, well, negative 6 over 14. And then we're going to have a 9 over 14. And then a 1 over 14. 3 over 14. Because 3 times 1 is 3. Yeah, just 1. And this one here, we could simplify this divided by 2. We got a 3 divided by 2 is going to be a 7. Like that. All right, or you can just write it as 3 times 2, this is 2 times 2, and this cancels. All right, so we're going to be left with this simplified even further, and this is all, I'll put it all over here actually. This equals to negative 3 over 7, 9 over 14, and 3 over 14, and this is our projection of B onto A. And yeah, this is our vector projection. All right, so now that we solved that, and let's go over the last section of this extensive video. So vectors in physics. So one use of projections occurs in physics in calculating work. So in my earlier video, we defined the work done by constant force F in moving an object through a distance d as work equals to force times distance, but this applies only when the force is directed along the line of motion. Suppose, however, that the constant force is a vector, we'll call this F, equals to PR. So it pointing in some other direction as in the figure below. And I'll draw this in a bit. So I'll draw this right here. So let's say you had, so if the force moves the object from P to Q, then the displacement vector is D equals to PQ. So in other words, let's say you had here's a displacement. So it moves along this direction from P to Q, but the force is at some angle across there. This is the vector F, and this right here is a displacement vector D. And then this right here is put a dashed line. This perpendicular, and this is going to be our S. This is going to be our R, and then we're going to have our other angle. Well, this is going to be our angle like that. So this is the PR. So this is the force F, the displacement from P to Q. But this force is at a different angle. Yeah. So our net force in the direction along the displacement is going to be this red one. Again, it's a projection of F onto this right here. All right, going further. So now the work done by this force is defined to be the product of the component, so this right here, of the force along D and the distance moved. So in other words, work is defined as equaling right here. So this is going to be the component onto this projection onto here, the component of it. So in other words, the magnitude of that force vector times by cosine to get the cosine direction of it. In other words, along this PQ, and then multiply the distance traveled, like that. All right, yeah, so that is the work. All right, so that is the work. But notice here, if you just move this distance D over in the front, and but then from definition 2 of the dot product, we have W is equal to, let's move this over here, and that just becomes the force magnitude times by the distance traveled, and then times by cosine theta. In other words, this is the dot product of force times the displacement vector, or the distance vector there. Yeah, so thus the work done by a constant force F, vector F, is the dot product of the force vector displacement vector, where D is a displacement vector, which is quite fascinating. So yes, we define a dot product, and then we somehow manage to link it all to physics and how work is defined. So you just use a dot product. Interesting. So continuing further, so let's take a look at example 7. So a wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. So we're assuming it's being pulled like that, 70 newtons, like that. The handle of the wagon is held at an angle of 35 degrees above the horizontal, and it asks find the work done by the force. And let's take a look at the solution. All right, so if F and D are the force and displacement vectors as pictured in the figure below, then the work done is, and let's just draw this is a straightforward one. It goes horizontal, so you have D like that. You have the force here, and the angle's 35 degrees. I'll just draw it like that. 35 degrees, this projection onto here. This is a right angle. This is our force vector. And what we get is, I'll smooth this over to here on the left side. So we get work equals, well, just a dot product. F times D, but we're given the angle, so we know angle. We know the magnitudes of both. This number here, this goes 100 meters, and the constant force is 70 newtons. So we get, this is going to be, I'll just put the magnitude of the force times by the distance traveled, or the displacement, and then cosine of the angle. This is going to be cosine theta, or cosine 35, like that. Or better yet, just put cosine theta. And then we'll put in all of our figures in. This equals to, or put it here, equals to 70 newtons times by 100 meters Yeah, like that, 70 newtons on 100 meters. And I'm going to move this here to have some more space. And then times by cosine 35 degrees. And if you plug this into the calculator, you get about 5734 Newton meters, which equals to 5734 joules, or J. Like that. So joules or Newton meters. Yeah, so unit of energy is just a unit of work there. Very fascinating stuff. All right, now that we have that, let's do a quick calculation check. So 70 times 100 times cosine 35. And if you just plug this in, this gets into joules there, which is fascinating. So yes, I think, yeah, this uses degrees. So yes, that is correct there. All right, continuing further. So example A, this is the last part or last question in this video. So a force is given by a vector F equals to 3i plus 4j plus 5k, so this is the standard basis vectors, and moves a particle from the point P, which is 210, to the point Q with the coordinates 462. And we're asked find the work done, and yeah, so find the work done in moving this particle from there using this force. So we have the distance or displacement we can calculate, and we have the force, and we can just find the work done. All right, so the displacement vector is, well, we're given, we can solve the displacement vector. Let's just solve this one first. So, and then we can do the dot product and solve it, but I want to graph it in a bit. So let's go to the displacement vector D. This equals to, well, distance, or the vector from P to Q, or the displacement there. I'm going to write this as equals to, well, it's going to be the difference. So difference from P to Q. So Q, you're moving from P to Q, so the displacement is the distance between it. So 4 minus 2, so subtract all the components. 4 minus 2, 6 minus 1, and then 2 minus 0, like this. So this equals to, well, 2, 5, 2, like that. That's the displacement vector. And this displacement vector is, again, is the relative distance from P to Q. All right, so thus the work done is, and before I do that, I just want to graph all of this in 3D just to illustrate what we're doing. And this is going to be our Z component. This is going to be our Y, and this is going to be our X. Like that. This is going to be our 0 origin. And we are going with a, let's get some points here. So we are going to be, the force is going to be in this direction, 3i, 4j, 5k. So 3i, so 1, 2, 3. Then 4j, it's going to be 1, 2, 3, 4, put it here, and then 5, 1, 2, 3, 4, 5, all the way up across on top there. And let's just draw this in 3D here. This one projected is going to be across here. This one's going to be across here, and it's going to look somewhere like this. So this is our force F, and then our particle is going to be moved from point P 210. So it's going to be 1, 2. Oh yeah, it's 2, 1, and 0. So it starts from here. That's our point P, and it's going to go all the way into, well, let's see where Q is. As 462. It's going to go to 1, 2, 3, 4, and then this is going to be, if this is 4 right here, 5, 6. Then 2, I'm going to go rise up twice. This is going to be somewhere across here. 1, 2. It's somewhere above here. So it's be a bit in 3D. It's going to be somewhere like that. So that is the distance here. Let's move it like that. It's just a bit hard to. That is our Q. And this thing is pushing it there. And yeah, that's what we have. So this is a displacement vector. And I believe we did, yeah, we do here this force, I assume it's just in the general direction like that. So you can just move it across here. And this is going to be just F. Just move it across there. So there's a force pushing in that direction like that. And yeah, I just wanted to show that anyway. So now we could just solve our product. I mean our dot product. So we can do that right here. W equals to the force vector times displacement vector, which equals 2, and this is going to be the force vector is 3i, 4j, and then 5k. In other words, in component form, 3, 4, 5, and then dotted with 2, 5, 2. 2, 5, 2. And this equals 2. Well, 3 times 2. I'll just put it all together. 3 times 2 plus 4 times 5 plus 5 times 2. This equals 2. 6 plus 20 plus 10. So it equals 36. All right, so that's 36, and it depends on the units. We're not giving in units here, but if I assume it's newtons and meters, we'll get joules. All right. All right, and here I'm just going to draw this parallel. So yeah, so if the unit of length is meters and the magnitude of the force is measured in newtons, then the work done is 36 joules. Again, that's just the basic physics units. Anyways, that is all for today. Hopefully you follow along another epic, long, deep dive journey into mathematics. Anyways, and yes, it helps helps me to learn big time. This is how I learn. I just go through it, make videos, and so on. Anyways, that is all for today. Let me just scroll all the way up, and I'll update the topics that it covers and timestamps because I added more headings as I went through the video. Anyways, that's all for today. And like always, you can download these exact notes in the link in the description below. And yeah, that's all for today. And also, make sure to check out my MES Links Telegram at t.me/MES Links. And I basically go through all my research in real time. A lot of funny stuff, a lot of conspiracy stuff, a lot of crazy stuff. Anyways, a lot of mathematics, science, and so on. Anyway, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.